In the previous chapter, we looked at, actually the last couple of chapters, we've looked at carbonyl chemistry a lot. We've looked at reactions occurring at the carbonyl carbon, specifically with nucleophiles attacking it. In this chapter, we're going to look one carbon away from that. We're going to look at the alpha carbon and reactions that occur there. So what do I mean by an alpha carbon? Well, we use Greek letters to designate positions as they move away from a functional group. So basically your alpha carbon is one carbon removed from your carbonyl carbon. And then if you keep on going outwards from there, you have a beta carbon, a gamma carbon, a delta carbon, and so on. Okay, so again, we're going to really focus on the alpha carbon here and the interesting chemistry that occurs there. All right, now to understand this, we first have to consider how aldehydes and ketones tautomerize. All right, now if you recall, basically we can shift over a proton in our molecule, shift it to the oxygen of our carbonyl, and shift where the double bond's located. And we call this an enol. Again, the ene part comes from the alkene part of that molecule, and the resulting alcohol group gives us the ol part of the name. Now, if you have trace amounts of an acid or a base to help catalyze this transformation, you'll establish an equilibrium between both forms of this molecule, the keto form as well as the enol form. Now, that being said, this equilibrium is usually shifted towards the more stable keto form, except for, well, a few exceptions. One of these exceptions here is where the enol form is kind of preferred, just because that sort of spreading out or delocalization of charge and the hydrogen bonding that's enabled by this enol form lowers the potential energy of this structure, makes it a little bit more stable. Another good example of where the enol form is oddly enough preferred is with a phenol. All right, with a phenol, having the aromatic ring over here is much, makes up for the loss of that stable ketone. All right, so I mentioned that this is catalyzed by any acid or base present. So let's go through how basically ketones and aldehydes tautomerize into enols. Okay, so if we're looking at an acid catalyzed tautomerization, we start off with a proton transfer to that oxygen on our ketone. Okay, and basically you put that positive formal charge, and that those electrons will swing up to that oxygen and move the positive formal charge instead to that carbon. Okay, so we have this sort of resonance stabilized cation that results, and so this is a relatively stable transition state. Now that being said, you can return this to a neutral molecule then by deprotonating that alpha carbon and forming the alkene part of our enol. In the case of base catalysis, the deprotonation occurs first. Our base plucks off that alpha proton, and now you've got a carb anion, which again is resonance stabilized. We can have those electrons swing up to the oxygen, and then that can get protonated to again give us the alcohol of our enol. All right, so tautomerization is something that happens, right? It's really easy to have this process occur, and we've seen that both cases, whether acid catalyzed or base catalyzed, have that relatively stable resonance intermediate, that resonance stabilized intermediate. And so the thing to keep in mind there is that even though we have a stable keto form, that enol form is a significant contributor. Okay, so even though you'd expect, that ketone to have, that double bond to the oxygen and more of that electron density to be on that oxygen, what actually winds up happening is you have this enolate intermediate where you've got a negative formal charge on that on that carbon, on that alpha carbon. Okay, so there's a little bit more electron density on that alpha carbon than you would normally expect in a ketone or aldehyde. Okay, so that being said, if you have an enol, it's very easy to deprotonate that alpha carbon because of that alpha carbon's ability to stabilize a negative charge so well. All right, it makes that alpha carbon relatively acidic. The conjugate base is relatively stable. Okay, and as I mentioned, we call that conjugate base an enolate. Okay, with that ate suffix to point out that it's got a negative formal charge. That negative formal charge, of course, is resonance stabilized. You can see here how we can shift that negative formal charge between the carbanion to that oxygen on our carbonyl. Okay, so with that in mind, the enolate can then act as a nucleophile, right? You've got a negative formal charge on your enolate, and that negative formal charge, that atom with a negative formal charge, can then act nucleophilic. It can attack some electrophile, and make a resulting product. Now, because that negative charge is, divvied up between both sides of that enolate, there are two approaches to this. You can have the negative formal charge in the oxygen and have the nucleophilic attack occur from there. Okay, so that's called an O attack. Or, of course, you can have it on the carbon for a C attack. Okay, now this might be a little counterintuitive because you might think, oh, that oxygen's better at stabilizing the negative charge, but it actually turns out that enolates prefer the C attack. Okay, if you want an explanation for this, you have to kind of go to hard, soft, acid-base theory, and in that definition, carbon is a quote-unquote softer base, typically what you would prefer in an SN2 mechanism. All right, so because of this, your alpha protons are very, very easy to deprotonate. They're pretty acidic when they form that enolate. Okay, you can remove them relatively easily. Okay, so let's practice this. Here is a molecule. Go ahead and identify the enolates you could form. So basically, look for any alpha carbons that might be easy to deprotonate, and go ahead and draw them in their deprotonated form. Okay, so if you pause this and come back, here are the two places where you could have done that. So you probably immediately notice this ketone over here, and probably realize, okay, well, you can't deprotonate this sp2 hybridized carbon because there's no protons on it. But this methyl group over here can easily be deprotonated, and here's the enolate that you can form. It's shown in its, with a negative charge on the oxygen, but of course you could also have the carbanion here, and that'd be fine. Over here is the other enolate, the other carbonyl, and there's the alpha carbon next to it that you can again deprotonate, and here's the enolate form. Okay, again with the negative formal charge of the oxygen instead of that carbon, but again you could draw it either way. Okay, so the nice thing here is that we now have an interesting source, interesting nucleophile to do a whole host of new reactions, especially because we have a carbon-based nucleophile. We've seen that this is very, very useful for forming carbon-carbon bonds, right? This is kind of our motivation behind Grignard reagents, for example, right? We like having Grignard reagents as nucleophiles because that allows us to extend the carbon skeleton of our molecules through a nucleophilic attack. Here we can do the same thing with these enolates. Okay, and enolates again are relatively easy to form. We just need to have a base present to deprotonate the alpha carbon on these ketones or aldehydes and convert them accordingly. Okay, now to understand the kinds of bases you need, let's first look at our pKa values, right? We need something that's basic enough to get that alpha carbon to act as an acid. Okay, so if we look at our pKa values, like for example here for acetone or acetophenone, we can see that those pKa values are in that 18 to 19 range, right? Just like a little bit over 19 for acetone here. Okay. In the case of acetaldehyde, that actually drops all the way to between 16 and 17. So let's look at an example of a base and see is this an appropriate base for for converting a ketone or aldehyde into the corresponding enolate. All right. So let's say we use sodium ethoxide. Okay. Um, so if ethoxide plucks off the proton on our acetaldehyde, it'll make ethanol. That's the corresponding alcohol. So let's compare pKa values for our acetaldehyde, which we established as 16.7, and for our ethanol. Now, alcohols in general have a pKa value somewhere around 15, 16, somewhere in that ballpark. And in the case of ethanol, it's specifically 15.9. Now, ethanol here, of course, is a better acid than acetaldehyde. So you can see that this equilibrium is, shifted to the left. It does favor our reactant. And so you're going to have more of your protonated version of your acetaldehyde and not as much of your enolate. Okay, so if you're trying to convert this all into enolate, then sodium ethoxide is not a good base for this conversion. However, if your goal is to have a little bit of both your protonated and deprotonated version of your aldehyde or ketone and your enolate, this actually works out pretty well. Notice that the pKa values for both our acetaldehyde and our ethanol are relatively close. So we do have an equilibrium here. This is not a reaction that goes in completion to the left, all right? Which can be an advantage, all right? Sometimes it's good to have both the aldehyde and the enolate present, okay? So remember, the aldehyde itself still has a carbonyl, which that carbonyl carbon is a good site for a nucleophilic attack. So, having a nucleophile and an electrophile present in solution would allow one to react with the other. So, again, sometimes that might be advantageous, right? You might be trying to make that resulting product. That being said, if you do want to have just the enolate present, you want to have a stronger base, okay? A good example of this would be hydride. So hydride is kind of advantageous here because when it plucks off a proton, it bubbles away as hydrogen gas. So this is kind of doubly irreversible. It's definitely going to be product favored because hydride is such a strong base, but even more so because there's none of that resulting product that's going to stay in solution to do the reverse reaction anyway. So generally, the enolate might be more useful than the enol. It's definitely a better nucleophile, right? You've got that better, that formal negative charge on that alpha carbon, right? And it's probably a little bit easier to store in its ionic form. That being said, something that's a little bit, that's more common is our what we call LDA. All right, so lithium diisopropylamine, amide, I should say. It's got a negative formal charge on the nitrogen. So basically, we've got these two bulky isopropyl groups, and it kind of makes this act just as a base, right? You'd want to avoid having a base that's too nucleophilic because it might attack that carbonyl of our aldehyde or ketone instead of acting as a base and making the enolate that we want. All right, so that's another reason why hydride, even though it's advantageous in that it kind of when it does act as a base, it goes on to to produce the enolate pretty, in a one-way reaction, but you also have to watch out for that side product where your hydride will reduce your aldehyde down to the corresponding alcohol. Okay, so that's something to watch out for. Okay, so we've seen that, generally speaking, the pKa's for most of these aldehydes and ketones have been somewhere around that 16 through 19 ballpark, right? We've got quite a bit of variance there. But one way to drastically reduce the pKa, okay, and therefore, change, the different bases that we could use that might be appropriate, is to actually have an alpha carbon that's alpha to 2 carbonyls. Okay, so here we have an example of a dione. Okay, we've got 2 ketone groups, and there's an alpha carbon in between both of them. Notice that our pKa drops to down to about 9. Right, so that's a pretty big jump there. Okay, you can see here how the reason for this low pKa is that the resulting enolate is resonance stabilized over multiple not just over 3 atoms but over 5 of them. Okay, so due to that low acidity, if we try using ethoxide again as our base, now notice that here our pKa for our for our ketone is much lower than that of ethanol. So instead of this being an equilibrium where we have both of our our ketone and our enolate present in equilibrium, this reaction pretty much goes one way towards the products, right? We only form this enolate. Okay, so again, you want to consider these pKa values. You want to think about the stability, the acidity of those ketones and the stability of that resulting enolate when selecting your base. Okay, so obviously here ethoxide, something like sodium ethoxide would be a perfectly appropriate base for making just the enolate here. But if we tried doing this with, a typical ketone or aldehyde, it wouldn't be. We'd have an equilibrium there. Now let's start looking at some of the reactions of enols and enolates. In a lot of these reactions, we'll see that alpha carbon, which is nucleophilic, will then act as a nucleophile. So in this first example here, let's look at halogenation. So our electrophile in this example is a bromine molecule. Okay, so we have our enol attack the bromine and kick off bromide as a leaving group. All right, again, a very good leaving group that's available there. And of course, you need something to deprotonate the resulting molecule to give you this neutral ketone with a bromine at that alpha position. Okay, and of course, you have HBr as your byproduct. All right, now if you have an asymmetrical ketone, where does the bromine go? Right? It turns out that you actually have it show up at the more substituted position, which initially might seem a little counterintuitive. You might think, oh, from a steric standpoint, why would this bulky bromine go over there? Remember, you're going through an enol intermediate, right? So you've got an alkene there, and if you have the alkene over here with the that methyl group there, that more substituted that more substituted alkene is more stable. So you're going through a lower energy transition state. All right, so that's why you tend to have this be the major product, even though it would appear that your bromine would have to attack a more hindered site, or rather, your bromine would add on to a more hindered site. Okay, so basically, since bromine, of course, is a good leaving group, you could then continue to kick off that bromine and do a dehydrohalogenation and make the corresponding alkene, specifically an alpha beta unsaturated alkene. You have to deprotonate over here, which makes sense because there's no proton here to remove, right? So you're going to form that alkene in the alpha beta, between the alpha and beta carbons. The other thing to notice here that makes this a very stable product is notice that we have a conjugated pi system in this process. Okay, so here's the full mechanism for that. You can see that in the second step we used pyridine as a non-nucleophilic base to help deprotonate at that beta carbon to go ahead and make that alkene. So again, here's the initial step. Again, remember when we start off with this keto form, this is we're going to actually use the enol tautomer to help with this. So basically, we go from the keto form, we protonate here using an acid, and we deprotonate at that alpha carbon to make the corresponding enol. Okay, and again, notice that this is we have our acid working catalytically here, right? The acid is regenerated in this step. Our enol, of course, then is our nucleophile. It picks up a bromine from a bromine molecule, kicking off a bromide ion. And of course, now we have a base here making the neutral keto form. But the key thing here is this step, where our pyridine base comes and deprotonates our beta carbon, and this in turn does an E2 elimination, right? So we have the hydrogen, our proton coming off, those electrons forming the double bond here, which in turn kicks the bromine off as a bromide leaving group. All right, and here's our final stable product. Another way to do this with much better yield and rate is the impressively named Hell-Vollard-Zelinsky reaction, or Hell-Vollard-Zelinsky halogenation, which is arguably the best name for an organic chemistry reaction ever. Basically, we have we include phosphorus tribromide, which goes on to form the acyl bromide as an intermediate. All right. Now, as we saw in the previous chapter, acid halides are very reactive, and so this kind of encourages the formation of the enol, and then once the bromine is on the alpha carbon, you can readily hydrolyze that acyl bromide back to a carboxylic acid. So here's the full mechanism explaining that whole process. So we can see here we start off with that carboxylic acid reacting with phosphorus tribromide, which we can then basically convert into this acid halide, acid bromide here, which then we can go ahead and tautomerize into our enol relatively easily. Once we have our enol, we of course can have that react with the bromine. As we've seen before, we have that attack the bromine, kick off a bromide leaving group, and make the corresponding substituted product. Right, we have a bromine substitute at that alpha carbon. Now, of course, in the second step, we are going to hydrolyze this down with water. Remember, this is very reactive, so even though water is a weak nucleophile, as we saw in the last chapter, we can readily convert this into the resulting carboxylic acid. Okay, so we've seen all these reactions occur under acidic conditions, right? We've seen that we need that enol present, and having an acid present to catalyze that tautomerization is necessary. Remember, we can also do, we can also have tautomers form under basic conditions, and so these alpha halogenation reactions can also occur under basic conditions. If this is the case, what happens first is you go through that enolate intermediate. So your base comes in and deprotonates that alpha carbon, making the resulting enolate. Again, your enolate's a great nucleophile, and it attacks that bromine and kicks off that bromide leaving group in the same way as before, and you go directly to your product that way. Okay, so that being said, oftentimes doing just having one of those protons swap out for a halogen is not likely. Like if you have multiple protons present, you tend to have multiple substitutions. All right, so in the case of a methyl group, this is especially apparent, right? So if you have a methyl ketone, you can substitute all three of the protons on that alpha carbon for a bromine. All right. What then happens is that becomes a good leaving group. You have a tribromide methyl group, which is easily cleaved off as a bromoform. That's CBr3H. All right. So it's like chloroform, but with a bromine instead of a chlorine. Okay, so you've got this great leaving group that leaves as CHBr3, and you basically you have water as a nucleophile doing that, and so you basically make the corresponding carboxylic acid, and you have that CBr3H or CHBr3, the bromoform, usually precipitates out, right? You've actually seen this reaction before in lab. This is a great test for methyl ketones. Typically, you use iodine to do this, and the resulting product is iodoform. So you've heard of the iodoform reaction or the iodoform test for methyl ketones. Well, this is basically how it works. Okay, so here's the mechanism once you've done the multi-substitution with halogens. So you've got 3 halogens here on your carbon. So you've got that tribromo methyl group here. So you have your nucleophile coming in. Oh yeah, this is under a basic condition. So actually, you don't even need water to be your nucleophile. You've got hydroxide as your nucleophile. So that attacks your carbonyl carbon, and it kicks off this great leaving group, which can be readily protonated to leave as bromoform. Since your bromoform is kind of precipitates out of solution, it's kind of pretty much insoluble in your solvent. This step is essentially irreversible, right? You don't have this acting as a nucleophile and doing the reverse reaction. And so as I mentioned earlier, you can do this with pretty much any halogen, not just bromine, and as a result, you get either chloroform, bromoform, or in the case of iodine, iodoform. And iodoform is a very bright yellow precipitate, as you guys have seen in lab before. So it's a very recognizable test for the presence of a methyl ketone. So if you have some carbonyl with a methyl group sticking off of it, it's a great opportunity, a great test for that. All right, so so let's practice this. Here's a ketone. Go ahead and draw the product for the reaction below. Okay, so if you pause this and taken a crack at this problem, hopefully, in addition to this methyl group that you've noticed over here, please note that there is a hydrogen on this alpha carbon as well. So don't forget that can also be swapped out for a chlorine. Okay, the question says to be careful of stereochemistry. I think that might have been a mistake, just because this cyclohexyl group is symmetrical, so this isn't technically a chiral center. This is going to be meso along that around that carbon, right? If there were a substituent somewhere, on any carbon of this cyclohexane except maybe this one, then yes, that would be asymmetrical, and this would be a chiral center, but I don't think you actually have to worry about the enantiomer, so to speak, here. The quote-unquote enantiomer of this would be the same molecule. Anyway, that being said, the key thing to notice is, of course, you do get a chloroform as your byproduct. So basically, this methyl group has all 3 hydrogens swapped out for chlorines, and then it leaves as chloroform. And in the process, you've hydrolyzed this into the resulting carboxylic acid. Like I said, I think that the part that most students would get wrong here is forget that there is a hydrogen on this carbon that does get replaced for a chlorine. Okay, so that brings us to aldol reactions. Basically, if you have a carbonyl compound, you have to realize that when that alpha carbon can be turned into a nucleophile, as an enol or an enolate, the carbonyl itself is also an electrophilic site. So you can have an aldehyde or ketone react with itself. One equivalent react with another. And as a result, you make what's called an aldol. You have the aldehyde half of it, all right? So that's from the nucleophilic molecule. And the carbonyl on the electrophilic molecule basically gets converted into an alcohol, and that's the all part of an aldol. Okay, so this alpha carbon, which is nucleophilic, especially if you're able to deprotonate there, that attacks the carbonyl on another molecule, and of course that's where you form the resulting alcohol. Okay, so let's have a look at how this reaction works. So in this case, we have a base present to deprotonate that alpha carbon, turning it into an enolate, which is a good nucleophile. That nucleophile attacks that carbonyl carbon, kicking those electrons up to the oxygen. You can then protonate that oxygen, and that gives you the resulting aldol. Okay, quick note here about locations. That alcohol is present on, essentially on the beta carbon, or what is now the beta carbon, to that original carbonyl. So that's a quick way to identify the products of this reaction. Look for a carbonyl and look for an alcohol group that's 2 carbons away. Okay, so this is kind of an equilibrium process. You might have the reverse reaction go back to the original aldehyde. So keep in mind that this reaction is reversible. It's not necessarily one way. So typically it looks like we have favoring of the products here. Okay, there are some cases where the product isn't favored, that the equilibrium is favored towards the reactant. This is especially in the case of ketones. So you've noticed that in the previous examples we used aldehydes as our carbonyl source. You could use a ketone, but the problem is that you don't get a very good yield. The equilibrium tends to favor the reactant there. Okay, so here's the mechanism for that reverse reaction. So here's our corresponding aldol, or I guess ketol product. And so here's the reverse reaction. So your base comes in, deprotonates your alcohol. Those electrons swing downwards to reform that carbonyl, which in turn breaks this carbon-carbon bond, forming the an alkene here, which shifts these electrons up to that carbonyl's oxygen. Okay, so you have this group leave as the resulting carbonyl compound, the corresponding ketone, and here you have an enol with the oxygen housing that negative charge. So if those electrons swing back down, you can do kind of like the second half of a tautomerization, but basically protonate that alpha carbon to give you the other equivalent of the ketone. Okay, so let's practice this. Here is an example of an aldehyde. Go ahead and draw out the aldol product for this, and draw out the mechanism too. This is a good chance to practice that mechanism and see what that looks like. Okay, so hopefully you've gone ahead and done that. So let's have a look at the mechanism here. So we have our base coming in, deprotonating that alpha proton. Okay. And so now that that resulting enol can attack a carbonyl and another molecule, right? So when it does that, it converts this carbonyl oxygen into, well, eventually that'll get protonated into our alcohol. Okay, so here is the resulting product that we get. Please note that this carbon is chiral, right? We have 4 different groups coming off of that carbon, so that is a chiral center, and so you get a racemic mixture of products there. Now, to take this one step further, your aldol product can go a further elimination reaction. We can do a dehydration or a condensation reaction to eliminate water across our alpha and beta carbon. So we essentially remove our alcohol group and a proton on our alpha carbon, and we make the corresponding alpha-beta unsaturated aldehyde. Right? So note that this is we've got a conjugated pi system. This is particularly stable. This reaction is known as an aldol condensation, right? Because we're making water as a byproduct. Okay, so this is a pretty easy to form product to sort of continue on with your aldol reaction. Okay, this can be either acid or base catalyzed. You can either start it off by protonating this alcohol group to make it a better leaving group, or you can use a base to deprotonate at that alpha carbon, and that can kind of initiate an E2 mechanism. Either way, whichever one works, you're going to form that resulting alpha beta unsaturated compound. All right, I mentioned that we can, do this under either acidic or basic conditions, and I kind of walked you through how to initiate each of them. So let's have a look at the full mechanism. So here, in the case of a base, as I mentioned, you start off by plucking off that alpha proton. All right, so that essentially is your E2 elimination mechanism. Okay. Over here, with an acid catalyzed reaction, you want to start off by protonating that alcohol group to make it a good leaving group. So again, you can have water coming in as a weak base and doing an E2. I suppose it could also go via an E1 by having that leaving group leave first. But anyway, the bottom line is that you have to start off with that proton transfer as your first step. Okay, so regarding the stereochemistry of your product, as you can see here, we have, your alkene can be either trans or cis. That being said, the trans isomer is going to be the more stable one, right? It's going to be your major product for two reasons. One, from a steric standpoint, obviously you've got your bulkier groups further apart, so it's better to have them trans to each other. From an electronic standpoint, if we go back to the mechanism, note that in the formation of the trans product, your proton and your leaving group for either mechanism are anti-periplanar to each other. So if you go back to our chapter on elimination reactions, you'll see why that's important. Okay, so that being said, because this condensation reaction happens so readily, and you often have, when you're doing your aldol reaction, you're doing it in the presence of, an acid or base, it's really hard to isolate just the aldol product. It often goes straight to your condensation product, right? You can see here in this example, we've got an extended conjugated pi system that's really, really stable. So it makes sense that this intermediate doesn't get isolated; it goes straight through to that final product. Okay, now. At low temperatures, so typically you favor the condensation product at high temperatures. So at low temperatures, it might be, it might be possible to get some more of the aldol product, but again, you're still not going to get good yields of it. All right, so that's the case here. So you can see with our at a lower temperature, we get the aldol product, but it doesn't go on to the condensation product, but it's still a relatively low yield. Okay, so let's try another reaction here. So go ahead and pause this video and see if you can predict the major product of this reaction. Okay, so if you've come back from now, here's the answer. Okay, so we're basically, please note that we're doing this with mild heat. So again, these are relatively mild conditions. So in this case, it looks like it stops at the resulting, aldol product. It doesn't go on to the condensation product. Okay. All right, now in the examples we just did, we used, just one aldehyde and it reacted with itself. So it made essentially one aldol product. What happens if you have two aldehydes present? Well, there's four possibilities, right? You could have aldehyde A react with itself to make one product. You could have aldehyde B react with itself to make another product. You could have A act as a nucleophile for B, or you could have B act as a nucleophile for A. And as a result, you have four different possible products. Okay? Now, from a synthetic standpoint, that's pretty lousy, right? You're going to get low yields of each of these because you're splitting your products into four potential products. So whichever one of these you're actually interested in, you're getting probably at best somewhere in the ballpark of 20%, right? So again, not very practical. So how do we increase the odds of getting the product that we want? Well, one way to do this is to select something that's not going to act as a nucleophile. It's only going to act as an electrophile. So in the case of formaldehyde, there are no alpha protons. You can't convert it into an enolate, and therefore it can only act as the electrophile. So in other words, this aldehyde over here is going to have this alpha carbon be its nucleophile, and it's going to attack that carbonyl. So you have to get this product. Of course, that's and here's another example. In this case, we've got a benzene ring. Again, there's no nucleophilic proton there's no proton on the alpha carbon, so you don't have a nucleophilic alpha carbon, and therefore this has to be the electrophile only. Okay. In this case, though, of course, you don't isolate the aldol product. It goes on to the resulting aldol condensation product. Again, notice that has a conjugated pi system. Again, though, in terms of synthetic utility, you have to hope that, okay, these are the types of electrophiles I want, right? What if you have electrophiles or a molecule you want to be the electrophile, but it does have alpha carbons, right? How do we do that reaction? And the answer is to do it in steps and basically figure out which, once we know which molecule we want as our nucleophile, start off by turning it into a nucleophile. So, in other words, form an enolate. Instead of using two enols, convert the half that we want to be and our nucleophile, make that the enolate first, and then add your second aldehyde in the subsequent step. So in this example here, we want to turn this ethanal into the corresponding enolate. So we use LDA as our base to do that, and then we add in this propanal as our second substrate. Now this is going to do its nucleophilic attack on that selectively. Okay, and so you exclusively make this product. So when you're trying to design a synthesis for a product like this, you look at this product and you say, all right, I've got my alcohol group over here. I know that this half of the molecule is what I wanted as my electrophile, and so that's the one you have to add second. Okay, so with that in mind, look at this molecule over here. Now, notice that we have an alpha, beta, and saturation, right? We've got an alkene across the alpha and beta carbons. So clearly this is a condensation product. So with that in mind, see if you can figure out what the aldol product looked like, and think about how you might design a synthesis, okay? And how you would specifically get this resulting product. Okay, so if we work backwards, here's what the aldol would have looked like, right? So you know that you've got an alcohol group at that beta carbon, right? So that carbonate, that beta carbon, was originally the carbonyl carbon of this half of the molecule. So that's what that looks like. And we know that that had to be our electrophile. So we know that's going to be the reagent as drawn. So using the rest of the molecule, we know that this carbon, this alpha carbon, had to have been turned into that resulting enolate. Okay, so here's the the enolate with the negative formal charge on the oxygen, but again, you could have drawn it the other way around with the negative formal charge on the carbon if you want to see that better, and then just tautomerize it into this. But then, of course, to look at what it looks as a neutral molecule, you accordingly just protonate that carbon, and here's the neutral starting reagent. Okay, so with this in mind, you can also have intramolecular reactions that can form cyclic aldol condensations. Okay, so here's a good example of that. So here we have one molecule with two ketone groups, and there are two alpha carbons present, right? So one of them can act as can be deprotonated and turned into your enolate nucleophile, and it can attack the other carbonyl to form this ring. Okay, and of course that would give you the aldol product. You can then continue to do the condensation, and again notice that you have your conjugated pi system within a ring here. Okay, and these are locked into that S, S trans configuration. All right. Now, in this example, we've got two ketones, and we just pointed out earlier that ketones aren't, don't do this as well as aldehydes. What gives here? Well, one of the things that helps drive this forward is the stability of this ring. So typically, if your intramolecular aldol reaction will produce a 5 or 6 membered ring, that's generally favorable from a stereochemistry standpoint. Okay, so that's something to keep in mind. Like aldehydes and ketones, esters can also undergo reversible condensation reactions, where we have the alpha carbon of our ester acting as a nucleophile, attacking the carbonyl of another ester. The key difference, though, here is that our esters have a leaving group, an alkoxy leaving group, right next to the carbonyl carbon. All right, so here you can see that our ester can be deprotonated at the alpha carbon, just like we've seen with our aldehydes and ketones. We make the corresponding enolate. That carbon nucleophile can attack the carbonyl carbon of another ester. Okay, now when instead of just protonating this and turning this into the alcohol of an aldol, what happens is these electrons swing back down, as you can see here, and kick off that alkoxy leaving group as an alkoxide. Okay, so you make this beta keto ester, right? So you have an ester here, and then here's the alpha carbon, here's the beta carbon. You have a ketone group at that beta position, okay? The alpha carbon here is alpha to 2 carbonyls, which remember makes this the protons on that alpha carbon particularly acidic. They're relatively easy to deprotonate. In fact, an alkoxide group is a strong enough base to deprotonate this, and so you'll actually get a pretty large yield, large percentage of this enolate ion in equilibrium. This is kind of favored by this equilibrium. All right, so if you do want to try and make this neutral product, it actually helps to add an acid to help protonate that site. Okay, so with this condensation reaction, there are a few limitations. There are a few things you have to keep in mind when you're looking at this from a synthetic standpoint. First of all, your starting ester should have 2 alpha protons. Okay, basically one of the things, since you have so many reversible steps, what helps drive this reaction forward is the removal of that second proton. Okay, you can't use hydroxide as your base. If you do, you kind of get a hydrolysis reaction. You wind up getting the corresponding carboxylic acid. So again, you're kind of losing yield there. And finally, the third point is actually kind of tied into the second point. The reason you can't use hydroxide is because you could have that OH group swapping out for your alkoxy group, and you get that carboxylic acid. In the same way, you don't want other alkoxy groups swapping out for the alkoxy group in your ester. So it might help to use the alkoxide equivalent of that alkoxy group as your base. Okay, so for example, if your ester has an ethoxy group as that OR group, right? So the R part of that is an ethyl group. It might be useful to have sodium ethoxide as your base. Okay, now just like you can do crossed aldol reactions, you can also do crossed Clasons. So basically, I just realized I said Clason. I've been saying Clason this whole time out of habit. Again, I think the proper German way to pronounce that is Kleisen. So bear with me with my inconsistent pronunciations of Kleisen. But anyway, with this crossed Kleisen reaction, we can basically you can have different alkyl groups attached to your esters, right? And you can combine these in different ways to get different products. Now, because we've seen with our crossed aldol reactions that we might get too many different variations and therefore get lower yields of the type that we want, it might be helpful to selectively choose reactants that have only one molecule acting as the nucleophile. So for example, here, notice there are no alpha protons to deprotonate. So this molecule can't act as your nucleophile. It has to be this molecule that gets deprotonated here and then attacks that carbonyl. And that's what we see here. Okay. Or if we do have multiple esters that we want to use that have alpha protons that can form enolates, we might select the one that we want to make our nucleophile and treat it with LDA to selectively deprotonate it. And then we know that that's going to be our nucleophile, and then add in our second ester, to have that be the electrophile. Okay, so we can do an intramolecular version of Claisen condensation here. You can have the basically have your nucleophile and your electrophile within the same molecule. All right, so you can see here basically carbon number 2 is our nucleophile, and it connects to carbon number 6. So that makes a 1, 2, 3, 4, 5 membered ring that we see over here. Okay. In situations like this, it's often very useful just to number the carbons just to keep track of everything. I highly recommend that. You can see here how easy it is to figure out where your different groups are on your product. The name for this intramolecular ring-forming Claisen condensation is called a Dieckmann cyclization. And here's the transition state for this particular reaction. So you can see here we have the formation of that carbon-carbon bond that closes the ring, and you can see kind of like the so the breaking of those pi bonds and the delocalization of all the electron density, right, from going from one carbonyl to the other. All right, so let's try some practice problems here. Here are some examples of Claisen condensation products. Again, a quick way to tell that you're dealing with that is look for an ester group and then 2 carbons away see a carbonyl. That should tell you that this beta keto ester is the product of this Claisen condensation. So okay, here's your ester group, and 1, 2 carbons away, here's that ketone. Okay, so go ahead and figure out what the original esters look like. Okay, so if you've paused this video and come back, here are the products. Okay, so you can see in this one, notice that we have a Dieckmann cyclization product, right? We've formed a ring here where our ketone is part of that ring. So that tells you that this carbon here was the nucleophile in our enolates. So again, if you're having trouble seeing this, like how to get from, get to this product from this reactant, try numbering the carbons here, and then that'll help you when counting out the carbons in between here. So basically, if we know that this is our nucleophile, so we have 1, 2, 3, 4, 5, 6 carbons till we get to the carbonyl that's our electrophile. So likewise here's our nucleophile, and we've got 1, 2, 3, 4, 5, 6. There's our carbonyl. Okay, and again here you can see that one of the things that if you're not sure what this alkoxy group is going to be, it helps to just use the same one, and keep in mind that when we're using a base for this, to use that same alkoxide as your base. Okay, so here we've got tert-butoxy groups, so that's why sodium tert-butoxide is the base that they're using. Okay, over here, again, if you have trouble remembering which one's your nucleophile, which one's your electrophile, remember your nucleophilic ester is the one that keeps the ester group in your product. Okay, it's the ketone part of your keto ester that's the electrophilic one. Okay, so we know that this carbon over here that's alpha to that ester group, that was the nucleophile. Okay, so if we were to break this bond here, this is what our original molecule looked like. So you treat it with LDA to convert it into an enolate, to deprotonate that alpha carbon, and therefore turn that into a nucleophile. And then you look at the rest of that molecule and say, all right, this is my carbonyl group. I'm going to add an alkoxy group to that to turn it into the ester that we need. And that's what we've done here. Okay, so our alkoxy groups here are ethoxide groups, ethoxy groups rather. And so that's why we've just added an OET here. Okay, so Now we've seen that through all these reactions that alpha carbon is very nucleophilic, right? We can easily deprotonate it. It's pretty acidic, but in all these reactions, we've been essentially using it as a nucleophile to attack another carbonyl. All right. Well, we've also seen that nucleophiles can do nucleophilic substitutions. That's one of the earliest uses we've seen for nucleophiles way back last semester, right? Early last semester. And so that's no different here. We can take our alpha position, our nucleophilic alpha carbon, and have that do a nucleophilic substitution on an alkyl halide. What this does is it kicks off that halide leaving group, which is a great leaving group, and it adds the alkyl part of that to that alpha carbon. Okay, so you can see here we can convert this ketone here into a nucleophile. We can deprotonate that alpha carbon pretty easily using LDA. We've seen that's a great base to do that. And then we add our alkyl halide to it. You can see that here that resulting enolate will attack that alkyl group, kick off that leaving group, and now notice that that alkyl group is just tacked on to the alpha position on our original molecule. Okay, now that was the case of a primary alkyl halide. We've seen that primary substrates are good for SN2 mechanisms. What if you use a secondary or tertiary alkyl halide? Well, in that case, your enolate might act more as a base than a good strong nucleophile, right? So instead, what happens is you actually wind up doing an elimination reaction, and you make the resulting alkene. Okay, so yeah, so basically, another thing to watch out for from a synthetic standpoint is that you have to watch out for your nucleophile reacting with itself. So remember, you still have a carbonyl on your ketone. So it might help to use a strong base, your LDA, to completely turn all of your ketone in nucleophilic, to basically deprotonate your entire sample of that before you add the alkyl halide. Okay. So yeah, and so another thing to watch out for in the example that we looked at, that was, so if I go back a slide, you can see here, this is a very symmetrical molecule. So whether I deprotonate this alpha carbon or this alpha carbon, it comes to the same thing, right? You're still going to get this enolate. But if you have an asymmetrical one, you've got to think a little bit about regioselectivity, right? Which alpha carbon is going to get deprotonated. Okay, so let's look at an example here. Let's say we have a ketone that already has a substitution on one of those carbons, right? So here we have an alkyl group present on this carbon. What's going to happen when we treat this with LDA? Well, we could deprotonate the carbon on the right, okay, and so the resulting enolate we'd make would have partial double bond character over here on this side. Notice that this alkene is more substituted because that carbon has that alkyl group on it. Okay. Of course, if we deprotonate the other alpha carbon, if we deprotonate one of these protons over here, we would have this less substituted alkene as part of our enol, or enolate rather. Okay, so the difference between these two is that this is the thermodynamic enolate, right? This is going to be more thermodynamically stable. We've got a more substituted alkene. And over here, we have the kinetic enolate. The reason that this is the kinetic one, remember, this carbon over here doesn't have an alkyl group blocking access for the base coming in to deprotonate that carbon, right? So here, there's one proton, and this alkyl group's kind of, sterically hindering access to it, whereas here you don't have that problem. Okay, so if you want to visualize this, you can see the difference here, right? That kinetic enolate has a lower energy transition state, right? Because there's less of that steric hindrance, when it comes to deprotonating that alpha carbon. But notice it's not as stable as our more substituted alkene, right? This is more thermodynamically stable. So you can see that even though it has a higher energy transition state, because of that steric hindrance, the resulting product is at a lower potential energy. Which, again, remember, this hopefully this sounds familiar when we think about the general difference between kinetic versus thermodynamic products. Okay, so if you recall, temperature affects which product you typically go for, which pathway you go for, right? The kinetic product will form under lower temperatures, whereas if you're at a higher temperature, typically you're providing your reactant enough energy to overcome the higher energy transition state of the kinetic of the thermodynamic product, and that's why a higher temperature usually gives you the thermodynamic product. The other thing to watch out for when listing out your reagents and your reaction conditions is that if you are trying to make the kinetic product and you're doing this at a lower temperature, you're going to need a stronger base to accomplish this, right? Remember, doing this at a lower temperature, while it does select the kinetic product, you still are lowering, the overall kinetic energy of your reactant, and you're just slowing down the rate of your reaction, right? So to enable this reaction to happen at low temperatures, you do need a stronger base like LDA. For the higher temperature, you can use a milder base like sodium hydride. I mean, I say milder, I mean sodium hydride's still a pretty decent base, but it's milder than LDA. Okay. Another thing to watch out for in terms of the overall, the net effect of these is that the reaction to make the kinetic product is an irreversible one. You're using that strong base, it's going to irreversibly make that kinetic product. Whereas in the case of using sodium hydride, under room temperature here, this is a reversible reaction. Okay, so let's practice this. Go ahead and try to synthesize this molecule here. Notice that we have lots of carbons present. You're going to try to start this off with carbon fragments of 5 carbons or fewer. Okay, so if you pause this and have come back now, let's see if we can go over the answer. Okay, so you actually start off with, this is your starting point, right? So here we have this fragment with our carbonyl over here, right? Which makes sense, right? Because that's what we're going to turn into our nucleophile. So if we look at the alpha carbons here, basically, this alpha carbon, we've got an alpha carbon here and an alpha carbon here. If we consider that this is our smaller group, we've got 1, 2, 3, 4, 5 carbons here, we could leave this isopropyl group intact as our starting material, as they've done here. So what we're doing now is we're adding the rest of that alkyl chain at this alpha carbon. So in each of these steps, we're adding each of these alkyl groups to the carbon on the left. Now this is the less hindered carbon, so we're going for the kinetic product here. We're going through the kinetic enolate. So I believe up here they've actually made a mistake. They've put sodium hydride here. I think they meant to put LDA at a low temperature. That's where you would add, to this less hindered carbon on the left. Okay, so if you did this problem and you saw this slide and you saw, wait a minute, they used a different base, I think that's a typo on their part. So if you selected LDA here at a low temperature, I think that's going to be the correct answer. But anyway, here's the ethyl group and the propyl group that they've added in each of these steps using those alkyl halides. Yeah, and there's your answer. Okay, so in another common synthesis that you might come across is the malonic ester synthesis. So basically, you can convert an alkyl halide into a carboxylic acid with 2 extra carbons that come from your malonate. Okay, your diethyl malonate is the ether that you start off with to make this. All right, so basically you start off with diethyl malonate. You use a base, and as we've seen before, it sometimes helps to use the base that's the same as your ethoxy group. So we're using sodium ethoxide as our base. It'll selectively deprotonate that alpha carbon that's in between both of your ester groups, and so readily forms this this corresponding enolate. Now, that is your nucleophile, of course, which will react with your alkyl halide and swap out, basically it'll tack on that alkyl group at that alpha carbon. If you heat this up with dilute acid, you will basically hydrolyze this to your to the corresponding diacid, okay, which you can then continue to heat, and it'll get rid of 1/2 of this molecule as carbon dioxide, and the resulting product will then tautomerize into a carboxylic acid, and there's your final product, right? So you've got that alkyl group that you got from your alkyl halide, and 1/2 of your malonic acid for your diethyl malonate is what adds on the 2 carbons with the carboxylic acid that we mentioned. Okay, so yeah, so that's the whole mechanism, but like I said, the shortcut is just realizing you're basically adding on this half of the molecule, and you're swapping this ethoxy group for an OH group to make this a carboxylic acid. So with your alkyl halide, so here we have a benzyl bromide here. So this benzylic group is tacked on to that carboxylic acid with another carbon on it. Okay, and so here's the resulting product we make. Okay, again, you can see the choice of base we've got here is sodium ethoxide. All right, now that swaps out one alkyl group. It's actually possible to swap out 2 alkyl groups before you get to the hydrolysis step at the end. So you can see here in 2 subsequent reactions, we've added on 2 alkyl groups. Okay, now keep in mind this is not going to be very necessarily clean. You might get a mixture of products here, but this is one way to, you can isolate this before you move on to the hydrolysis step. Okay, another similar reaction is the acetoacetic ester synthesis. All right, so it kind of does a very similar thing, except instead of making a carboxylic acid, we make the corresponding ketone. It's basically a methyl ketone here. Okay, so so instead of the OH group of our carboxylic acid, notice that we have a methyl group here. Okay, but the rest of this is pretty similar. We have a carbon and then the alkyl group that we got from our alkyl halide. So here's an example of the overall reaction. Instead of starting off with diethyl malonate, we're starting off with ethyl acetoacetate, right? That's what it's basically diethyl malonate, but with that methyl group here instead of another ethoxy group. Okay, but the reaction's pretty much the same. We're still going to use a sodium ethoxide as our base. We then add in our alkyl halide, and again, in the final step, we can hydrolyze this to get rid of that half of the molecule that has that ester. Basically, we hydrolyze that to a carboxylic acid and then get rid of it as carbon dioxide. And so essentially, we've tacked on this half of the molecule. This half of the molecule, including this carbon here, to that alkyl group from our alkyl halide. Okay, so here's the overall reaction if you want to see it. Our base, the ethoxide from our sodium ethoxide, deprotonates that alpha carbon pretty easily, and you make the resulting enolate, which that nucleophile will do an SN2 substitution and basically, tack on that alkyl group. Okay, we can then do our hydrolysis of our ester. So, basically protonate the carbonyl, have our nucleophile come in. In this case, our nucleophile is water because this is being done under acidic conditions. Our nucleophile comes in, and you could deprotonate this and reform the carbonyl while kicking off that ethoxy group as an ethoxide. and actually, I guess it's protonated here, so it actually leaves as ethanol, which is much more stable, which that makes sense. When you reform that carbonyl, you've made a carboxylic acid, and then you can rearrange this while kicking off carbon dioxide as as sort of your leaving group. And this reaction is irreversible. The carbon dioxide bubbles away, right? And so out of the resulting enol, this just reconverts into the ketone that we see in the product. All right. So we've seen in aldol condensations, we make the corresponding alpha beta unsaturated carbonyl, right? So remember, when we have an aldol, we'll have this aldehyde group, and then 2 carbons away at that beta position, we'll have an alcohol. Well, if we do a dehydration, so we get rid of that OH group and a hydrogen at that alpha position, we're eliminating water, and we make an alkene here. Okay, again, that's the condensation part of aldol condensation. Now, something to keep in mind with your aldol condensation product is that it's particularly stable. You've got this conjugated pi system, right? And the thing to realize then is there's a lot of delocalization of electrons. So you have lots of resonance contributors here. Okay, so you've got the neutral structure. You can get this sort of Zwitter ion here where that carbonyl, those electrons go up to the more electronegative oxygen. And of course that carbocation is resonance stabilized because it's essentially allelic. So you can have that resonance structure where the positive charge is delocalized over here. Okay. So that's something to keep in mind when we think about what might attack that molecule and where it might attack it. So, we've got some electrophilic, positively charged carbons, and both of those can be attacked accordingly by nucleophilic carbons or carbanions. Okay, so if we think about carbanions that are nucleophilic, we think of Grignard reagents and Gilman reagents. So in the case of a Grignard reagent, we typically see that alkyl group being added to the what was the carbonyl carbon. Okay. Now, contrast that with Gilman reagents. What we instead see is that the alkyl group adds on to that beta position. So we actually have the alkyl group over here. Okay, so that's something to keep in mind from a synthetic standpoint. Okay, so if you notice that we're starting off with an alpha beta unsaturated ketone or aldehyde, and you want to make something where you've got an alkyl group at either this carbonyl position, which now becomes an alcohol, right? An alcohol with, an alkene that's 2 carbons away. Or you want to try and do this 1,4 addition where we've got a carbonyl and then 2 carbons away we've got an alkyl group. Again, keep in mind that the difference there is whether you use a Grignard reagent or a Gilman reagent. So your Gilman reagent will form that 1,4 addition product. So you have that nucleophile essentially adding on to that beta position. Remember, your Gilman reagent is a little less nucleophilic than your Grignard. Your Grignard is very reactive. Your Gilman isn't as reactive. So in the case of a Gilman reagent, you go through this enolate intermediate, which is resonance stabilized, right? So you have this lower energy, more stable, intermediate that helps out that mechanism, right? So basically, the first thing that happens is that nucleophilic attack. You make this enolate, you do a proton transfer, make the corresponding enol, which then tautomerizes to give your product. Okay. In the case of a Grignard reagent, which is more reactive, it's going to instantly kind of react with that carbonyl carbon, which is, just more electrophilic, right? It's right next to that really electronegative oxygen. So the more reactive Grignard kind of just attacks it directly. Now, those are 2 examples of, negatively charged carbons as our nucleophiles, right? Remember, we can make enolates as well. Enolates have a negative charge on that carbon, or at least have a resonance structure that does. And so we can use those as our nucleophiles as well. Now, in terms of our sort of reactivity scale, enolates are kind of in between Grignards and Gilman. So you actually get a mixture of the 1,2 and 1,4 addition products. Okay, so while Grignards typically give you the 1,2 addition, Gilman give you the 1,4. Enolates will give you a mixture. Okay, so probably not as synthetically useful, right? You're going to get a lower yield of whichever one of those two products you want. However, if you use a doubly stabilized enolate, so if you have two carbonyls with a mutual alpha carbon, right? So the resulting enolate, the negative charge on that is kind of resonance stabilized across all of these atoms here. That enolate is stable enough that it'll more mimic the stability of a Gilman reagent, and so it tends to react at that beta position to make that 1,4 addition product. Okay, so to expand on that, generally when your enolate is your nucleophile and it's attacking the beta carbon of your whatever your electrophile is, we call this generally a Michael addition. Okay, so your Michael donors are your your enolates, which we've seen typically tend to be these doubly stabilized ones, right? So we have multiple groups on either side of that carb anion that help stabilize it. And in the case of Gilman reagents, well, also Gilman reagents are counted as Michael donors here. Michael acceptors, of course, are those alpha-beta unsaturated carbonyls. Now, what else is on that carbonyl can vary. We could have that carbonyl be an aldehyde group, it could be a ketone group, we can have an ester, we can have an amide, we can have a nitrile, so even doesn't have a traditional carbonyl, but it's still lumped in with those acid derivatives. And also we can have a nitro group here. Okay, again, with a nitrile or a nitro group, those are kind of taking us a little bit away from our traditional carbonyl based compounds. But again, we see similar reactivity there. We have that that beta position that is particularly electrophilic and welcomes an attack from those Michael donors. Okay, so here's an example of a Michael donor and a Michael acceptor. Go ahead and draw out a mechanism showing that. So I don't have an answer slide for this, but basically your nucleophile is going, you start off by drawing an arrow going to that beta carbon. Those electrons, you can have a curved arrow going here and one going here. So you've got, that basically that negative charge is on your oxygen. Okay, so that can pick up a proton and get stabilized into the resulting enol, right? So now you have a double bond here, and this is an OH group. But of course, you can tautomerize that back into the corresponding keto form. Okay, so basically, essentially what's happening is this carbon is connected here, and you're adding effectively a proton here and getting rid of this double bond. It's essentially this mechanism that we saw back here on this page, right? So your nucleophile here, your Michael donor, attacks that 4 position. Okay, you make the corresponding enolate, and then protonate that to the enol, which you can then tautomerize. And so here's the product. What the net effect is, you've essentially added your Michael donor to that 4 position, and you get rid of that double bond with a proton added to that alpha carbon. Okay. Now, we've seen that the enolates for our Michael addition tend to be doubly stabilized, right? That's what tends to make them stable enough to react in the way that they react, right? If we use a singly stabilized enolate, we tend to get a mixture of products because it's somewhere in between the reactivity of a Gilman versus a Grignard reagent. That being said, if you do want to use a singly stabilized enolate, another method to do this is to use an enamine intermediate. Okay, this is called a Stork synthesis after Gilbert Stork. So what we do is we start off with our, our carbonyl compound with its, alpha carbon that we're going to deprotonate to make our our enolate. And to do this, we're going to use an amine, right? Now, your amine your enolate can also attack that nitrogen. Okay, so you make the corresponding enamine when this happens. Okay, so here's so here's your enamine, and I want you to see the similarities here between your enamine and your enolate. Instead of the oxygen housing that negative charge, we instead have a nitrogen, but it again we notice that it doesn't behave exactly the same way, right? The nitrogen isn't as electronegative as the oxygen, so we don't actually have the nitrogen housing the negative charge as our enolate does, but it does help delocalize the electrons by contributing that lone pair over here and pushing electrons to that alpha carbon, and there is your slightly nucleophilic alpha carbon with that lone pair making a carbanion. Okay. Now notice that, so while I've pointed out the similarities, notice the differences here. We're starting off with a neutral molecule as opposed to our enolate, which is an ion. Okay. So the resulting, carbanion we hear is actually part of a zwitterion. We have a positively charged nitrogen in this process. Okay. As a result, this enamine, this carbanion that we form here is less nucleophilic than our enolate. Okay, and so unlike a typical enolate from just just the enolate that we have here, this one is going to be a little bit more likely to behave as a Michael donor. So just like all of our other Michael addition reactions, we have the lone pair on our Michael donor, attacking that beta position of our Michael acceptor, right? These electrons swing over here, and these electrons swing over here. We essentially form this enolate, right? Now, out of this resulting product, we can hydrolyze that iminium ion down. So we just treat this with dilute acid. And the water basically hydrolyzes that imine back into a carbonyl. Okay, and it also tautomerizes that enolate back into the keto form. Okay, now notice in this Stork synthesis where your keto groups, your carbonyl groups, are in relationship to each other. Okay. Actually, in general, with your Michael addition reactions, notice where how many carbons we have in between our two carbonyls. Okay, so if we count the carbonyls, so we've got 1, 2, 3, 4, 5 carbons, in between, or 3 carbons in between our two carbonyls. Okay, so let's practice that. So go ahead and see if you can make the resulting molecule. This resulting molecule using the Stork enamine synthesis. Okay, so notice again we have our two carbonyls here and 1, 2, 3 carbons in between them. Okay, so break this down and ask yourself which one was your, could be converted to your enamine, and what's your Michael acceptor here. All right, so here's the reaction. You can see here if we look at our two carbonyls. And we look at this one here. Basically, like for each carbonyl, we've got an alpha carbon here and an alpha carbon here. So it kind of makes sense that you'd want to have your Michael acceptor be this one on the right, because remember, we're attacking the beta position of our Michael acceptor. And in the case of this carbonyl on the left, that beta position's over here. So it doesn't make sense that, this was the Michael donor and this was the Michael acceptor. It must be the other way around, right? Because for this carbonyl, here's that alpha position, here's that beta position. So this is the bond that we're forming. Okay, so if you're going to break this apart into two pieces, one of them is this one here, which you can see as our starting reagent here, and our Michael acceptor is this half here with the double bond between these two carbons, and that's what we see over here. The Robinson annulation is another variation of the Michael addition. So basically, we start off with the Michael addition. So here, notice that we start off with our Michael donor as this doubly stabilized enolate. And here's our Michael acceptor, our alpha beta unsaturated ketone. So this is our nucleophile. It's going to attack that 4 position, that beta position, and make this corresponding Michael addition product. Now, notice that on our Michael acceptor, we still have an alpha carbon, okay? And this is still going to be nucleophilic. And notice its proximity to this carbonyl, right? So we can have this be our nucleophile, and that can attack that carbonyl here, okay, which will convert this into an alcohol group, which we can then basically do an aldol condensation. That alcohol group and the neighboring proton will disappear to make this, alpha beta unsaturated compound. Okay, so we have the Michael addition in that first step where we connect these two. The aldol condensation is further helped by the fact that we make this 6-membered ring over here. Okay, and again we also have this locked into place S-trans conjugated pi system as well. Okay, so this is a particularly stable product. Okay, so we've covered quite a few reactions in this chapter, but I'm hoping that you'll kind of see the similarities between all of them. Most of them involve forming carbon-carbon bonds, which we've seen are very, very useful, especially when it comes to extending the carbon skeleton of a molecule, right? So typically when we look at doing syntheses, those are kind of the two main goals here are either to extend the carbon skeleton or to change functional groups. Okay, that's another advantage here. Like the products that we've seen often involve multiple functional groups, so it's a great way to when you're trying to design a synthesis for something that contains multiple functional groups, it might be a good idea to sort of have the template of these products in mind and see, okay, does this product I'm trying to make fit into this template? Can I use this reaction to make the product I want to make? Okay. Now, you probably noticed earlier when I was talking about the storic-enamine synthesis and just like Michael reactions in general, that I pointed out the distance between the carbonyls, right? That's that's a generally good approach to figuring out if the molecule you're trying to make fits into a particular template. Look at the relationship between your multiple functional groups. Okay, so here's a quick summary of that, right? So with your storic-enamine synthesis, notice that your carbonyls are 5 carbons apart, or have 3 carbons in between them. With aldol and Claisen reactions, we have 3 carbons, or well, just 1 carbon in between, but they're at the 1 and 3 positions relative to each other when it comes to our functional groups. So, the case of our Claisen reaction, we have carbonyls at the 1 and 3 positions. In the case of an aldol reaction, remember you have an aldehyde group and an alcohol group. That's the all part. And again, they are at the 1 and 3 positions with only 1 carbon in between them. All right, so that's a quick way to recognize the approach you want to take to making a particular, to making a particular product. So if you notice that your product has an aldehyde or a carbonyl and an alcohol group with only a carbon in between those two, you can just do your typical aldol reaction. Okay. Again, and also this is with an aldol reaction. Keep in mind that we do similar approaches with aldol condensation. So in this case, we would have that alcohol group would be missing, and we'd have a double bond between carbons 2 and 3 if you do the condensation reaction. All right. We've seen, we've learned two methods of adding on alkyl groups, right? We could use our enolate as a nucleophile to do an SN2 substitution on alkyl halide, okay? Or we could look at our Michael reaction, right? Our Michael donor acts as a nucleophile on our Michael acceptor. It acts at that beta position, okay? Please note that you can combine these two, right? So, for example, we've seen that Gilman reagents are Michael donors, right? So that's basically going to add the alkyl groups on our Gilman reagent here. So this ethyl group would attack that beta position of our Michael acceptor here, this alpha beta unsaturated ketone. When it does that, it will remove this double bond. Now notice that this position here is alpha to this carbonyl over here, so that can also be turned into a nucleophile, right? So we can have that basically act as our nucleophile, because when you react this with a Gilman reagent, this turns into an enolate, right? That's one intermediate. So instead of like protonating that, you leave it as an enolate where it's still a nucleophile, and it will attack this methyl iodide and tack on this methyl group at that alpha position. Okay, so here's the full mechanism for it. So here's our Gilman reagent adding on that ethyl group as a carb anion nucleophile, right? When these electrons swing up here, you make this resulting enolate. Well, again, that enolate will react with, will be the nucleophile on our methyl iodide, kicking off that iodide leaving group, and we've tacked on that methyl group at that position specifically. Okay, so let's practice this. Here's a couple of molecules. So we're starting off with this starting material. We want to make this intermediate, and then take this and make this product, right? Go ahead and pause this video and see if you can figure out the reagents for this. Okay, so if you're back, please note that if we had an alcohol group at this position, this would be an aldol reaction. Instead, we have this alpha beta unsaturation, away. This alkene is just one bond away from our carbonyl. So that should immediately tell you you're doing a aldol condensation to get here. But before we get to that, you probably have noticed that that carbon skeleton's been extended. So that tells us that this part of the molecule, that carbon skeleton that's been added on, must come from the electrophile of our aldol condensation, right? That must be the part of our aldehyde that was attacked by this alpha carbon, right? So here's what that looks like. So we first start off with this half of the molecule. Okay, and we know that since that carbonyl is intact, that's that alpha carbon is there in what we're going to turn to our nucleophile. So we start off with this half of the molecule, reacted with LDA to turn, to deprotonate that that carbonyl, that alpha carbon next to our carbonyl, and then here's the rest of that molecule. We're going to have that nucleophile attack this carbonyl, right? And of course, the resulting product would have, an alcohol group here, and you don't have this double bond. But then, if we just, react with some dilute acid afterwards, we can, not dilute acid, just acid in general. But it will, basically you'll protonate that alcohol group, and you'll get that to leave along with a proton here to make this alkene, right? And so we have this alpha beta unsaturated ketone. Now, when you look at this intermediate compared to the final product, the difference here is that we've got alkyl groups added at the alpha position and the beta position. So to add on an alkyl group at the beta position, of course, we can use our Michael reaction, okay, using a Gilman reagent. So a Gilman reagent specifically will attack that beta position, and so we can use an ethyl group on our Gilman reagent. And subsequently, to add on this butyl group at the alpha position, we can just use that resulting nucleophile to react with butyl bromide, okay, or some butyl halide, to make that corresponding, to add on that alkyl group through a SN2 substitution. And that's it for this chapter. So With the end of this chapter, we're getting into our second exam, so be sure to, try the practice quiz for this chapter, and go through your old quizzes for the previous three chapters on chapters uh, 18, 19, oh, sorry, 19, 20, and 21, um, you know, as well as that practice quiz for chapter 22 to get ready for the exam. All right, so let's go through some practice problems, but of course, for the to get a hang of more of the procedural problems you'll get on your exam, your application type of problems that you'll see on your exam, be sure to try the homework out as well. Okay, so this is an example of a more declarative, just kind of why is this happening question, which again helps you understand the background information, but you're probably not going to get a direct question like this on your quiz or exam. Okay, so glossing over that, here's an actual synthesis problem that's a little bit more practical. So here we have this ketone. We're reacting with excess chlorine and sodium hydroxide. What's the product going to be? All right, so that alpha position will specifically be your nucleophile, and therefore prone to, basically tacking on a chlorine and kicking off a chloride leaving group. Okay, again, we have another, declarative problem. I'm going to gloss over that. All right, here we go. Here's another reaction. So here we're making this aldol product. Again, notice it's an aldol. We've got that alcohol group that's 3 carbons away from this carbonyl. So that should tell you, just looking at that, what your nucleophile and what your electrophile would be. What's the bond you're forming. So go ahead and predict the product, the reagents needed to predict this, to produce this product. Okay, so if you've paused this and come back, again, the fact that this carbonyl is intact tells you that this alpha carbon was the nucleophilic site, or the nucleophile that attacked this carbon here that would have been the carbonyl. So you're breaking this bond to get the original reactants. Okay, and here they are. I mean, they don't show it, but benzaldehyde is what this half of the molecule looks like if you convert this alcohol group back to a carbonyl. All right, so here's here we have ethyl acetoacetate, right? So again, that should immediately get you to think back to that ester synthesis. And so ask yourself, what would this react with? What's the electrophile this would react with to give us this resulting product? Okay, so you can probably notice that there's lots of things going on, right? This is a pretty complicated alkyl group. So we've got multiple steps going on here. So in the first step, we've tacked on an ethyl group over here, right? And basically, we can then tack on the rest of this molecule through basically a Michael reaction followed by, rather I should say an aldol condensation followed by a Michael reaction followed by a nucleophilic substitution. So we can get this tertbutyl group here added on, by using this aldehyde and do a subsequent aldol condensation. So if you're having trouble seeing this, let me draw the intermediates because I think that might make this a little bit easier to follow. So basically, after this first step, we have, so when we react this with sodium methoxide, we deprotonate over here, and that acts as a nucleophile and adds on this ethyl group, right? So our first intermediate looks like this. Okay, so there's that. Okay, so that's where we tack on that ethyl group. Okay, so then we subsequently hydrolyze that, and we essentially eliminate this. When we hydrolyze this with sodium hydroxide, we convert this into a carboxylic acid, and when we treat this with acid and heat, we clip off this part of the molecule here as carbon dioxide. Okay, so we convert this into an OH group as a carboxylic acid, and then we get rid of this in this step as CO2, And so we just have this half of the molecule left, right? Specifically, it's an enolate with a nucleophile at this position here. Okay, so at this point over here, we've made this molecule, okay, with our enolate over here. This can then attack this carbonyl over here, okay, and that's what's adding on this part of the molecule, right? So the intermediate we have here, especially once we protonate it, we will make, we basically, when we treat this with acid, actually here, tell you what, let me draw the aldol product first so you can understand where the condensation product comes from. So here is that OH group. Okay, so this carbonyl becomes an OH group, and here is the rest of this molecule. There we go. Okay, so this is the aldol intermediate that we get after this step. So we can then eliminate this OH and this hydrogen to make the corresponding alpha beta unsaturated intermediate. So basically, it looks like this. So we have our tert-butyl group. There's our alkene, and there's our alpha beta unsaturated ketone. Okay, so then in the last two steps, all we're doing is we're doing a Michael addition using our Gilman reagent. So remember, this Gilman reagent is specifically going to add this ethyl group to that beta position over here. So that's the ethyl group we see here. And then that turns this position, which is alpha, to this carbonyl. That's going to be an enolate that's going to be nucleophilic. And we get that to attack this methyl iodide and tack on a methyl group at this position, which is what we see over here. And that's how we add on all of those groups. Now, again, don't panic. This involved lots of steps. You're probably not going to see something quite this complicated on a quiz or exam, but this is a good summary of a lot of the different reactions we saw. And you can see really how you can set up a multi-synthesis, multi-step synthesis from your various reactions you've learned in this chapter. Okay, let's see another example here. Okay, so here again we're starting off with ethyl acetoacetate. Notice, by the way, that we have two carbonyls here, and there's 1, 2, 3, 4, 5 carbons involved in that chain. So there's 3 carbons in between the 2 carbonyls. So think about what that template fits into. Okay, so here you can see that we start off with our acetoacetic synthesis with we use sodium methoxide, we add ethyl bromide. So again, notice that we've got an ethyl group at that alpha position there. Okay, so again, very similar to the last problem where we're adding an ethyl group at this position here. Okay, and then hydrolyzing that to get rid of this as carbon dioxide. Now, notice that your terminal carbon here is not a methyl group like this, right? We've got another ethyl group tacked on here. So that's the reason for the second step is over here. It's to add another ethyl group. I'll tell you what, let me draw the molecules so you can not lose track of what's happening here. So in those first couple of steps, those first 3 steps, we're adding an ethyl group here and getting rid of this as carbon dioxide, right? So this is what our molecule looks like after these first 3 steps. So in step 4 and 5, I think I probably tacked this on because I think the original version of the slide had skipped this step. But basically, we want to deprotonate this less substituted carbon. So in other words, we want the kinetic enolate. So that's why we're using LDA at a low temperature. If we were tacking on another alkyl group here, we would use sodium hydride at room temperature. But instead, we want to deprotonate here. So we're going to use LDA at a low temperature, and we're using ethyl bromide, and that tacks on this extra alkyl group, this extra ethyl group, to make this half of our product that we're trying to get. Okay, so now for this half of the molecule, again, note that we are essentially, doing a Michael reaction. Again, notice the distance between these two carbonyls. So if we look at this half of the molecule, here between these alpha and beta carbons, we could consider this carbon here, right, one of these alpha carbons, which, by the way, this is completely symmetrical, right? So it doesn't matter which of these we deprotonated. Either way, we'll get this product. That alpha carbon is going to be our Michael donor. So what does our Michael acceptor look like? Well, we need a double bond over here, right? So we break this bond to see what the original molecule looked like, and we put a double bond here, and this is the alpha beta unsaturated ketone that we're going to use as our Michael acceptor. So this carbon connects over here, and eventually yields this final product. Okay, so that's it for this chapter. Good luck getting ready for your exam. As always, if you have any questions, just let me know.